Ratings. Our group consists of Samuel Tordesilla, Daniel Ospina, and me, Luis Segura. And the presentation is about the production and characterization of biomaterials, depending seminar. The general objective is simulate the mechanical properties of a biodegradable suture based on ovalbumin, selected through a literature review of materials to evaluate its availability as a proposal in tissue engineering through finite element analysis in ANSYS. And the specific objectives are the first is conduct a literature review on ovalbumin as a potential biomaterial for biodegradable sutures, identifying its properties, reported applications, and advantage over other materials. The second is theoretically characterize ovalbumin as a suture material, defining its mechanical parameters, biocompatibility, cytotoxicity, and the degradation capacity based on the literature. And simulate using ANSYS the mechanical behavior of an ovalbumin suture filament subjected to tensile loads, evaluating whether it meets the strength requirements for soft tissue. Okay, the surgical sutures are fundamental medical device used in millions of procedures worldwide for tissue closure. Despite their essential role in clinical practice, conventional suture materials, particularly synthetic ones such as nylon, polyester, and polylolic acid, present several limitations that can negatively impact the healing process. This includes lower non-ideal degradation rates, tissue reactivity, possible bacterial colonizations, due to surface properties and the generation of byproducts that may alter the local physiological environment and potentially leading to inflammation or delayed healing. Although these synthetic sutures are really preferred due to their high tensile strength and durability, they are biologically passive materials, and this means they do not actively contribute to tissue regeneration and functioning only as mechanical support for wound closure. In contrast, current strength in tissue engineering emphasizes the development of advanced biomaterials capable of not only closing wound but also promoting cellular activity, improving tissue integration, and accelerating the healing process. Research in biomaterials has demonstrated that materials showing promising results under controlled laboratory conditions in vitro do not always perform effectively in real biological systems or in vivo. The factors such as immune response, vascularization, and interaction with the surrounding tissues can significantly influence the final outcome. Um, Within this framework, the exploration of alternative biomaterials becomes necessary, and ovalbumin emerges as particularly promising candidate. Ovalbumin, the main protein found in egg white, is characterized by its high availability, low cost, and renewable origin, making it a sustainable and accessible resource for applications. Its protein-based nature also provides advantages such as good biocompatibility and low immunogenic response, and the ability to degrade into non-toxic amino acids that can be easily assimilated with the body. However, despite the advantage, protein like ovalbumin present in their eliminations, particularly in terms of mechanical strength and structural stability when used alone. These properties are critical for applications such as surgical sutures, which must withstand tension and maintain integrity through the healing process. For this reason, the combination of albumin with polyvinyl alcohol is proposed as strategy to enhance the performance. The PVA is a synthetic but compatible and biodegradable polymer widely used in biomedical applications. And moreover, the real literatures indicates that with albumin has been studied in different formats such as scaffolds, membranes, and reverse for tissue engineering.
Hi, this slide shows the main problem addressed in this study. Bone defects can be caused by trauma, disease, or congenital conditions. The test defects result in a loss of bone structure and fusion. In many cases, bone cannot heal properly on its own. The current gold standard treatment is use and autograft. However, this method has important limitations. Therefore, there is not developed and advances the biomaterials for bone regeneration. Okay, and this slide explains the justification of the study. Bond effect require effective strategies for regeneration because natural healing is limited. Current treatments, such as autograft, present important limitations, including limited availability and complication. Okay, for this reason, tissue engineering has emerged as an alternative approach. In this field, biodegradable scallops are used to support cell growth and tissue regeneration. In addition, bioactive coaching can be incorporated to improve cell adhesion and stimulate bone formation. Therefore, the goal of the study is to develop an scaffold with bioactive properties to enhance bone regeneration. Okay. Okay, this slide presents the material used in the study. The main material is biodegradable polymer KPCLTMA, which used to fabricate the scallop structure. The material is important because it can degrade over time and place beneath bone tissue. The scaffold is produced using 3D printing technology, specifically stereography, which allows precise control of the structure. Okay, this is important to mimic the architecture of natural bones. This is very important. Okay, in addition, the scaffold surface is modified using different bioactive coatings. These include elastin-like polypeptides known as LP, which improve biocompatibility. Another coating is a combination of polyethylene acrylate, fibrocnectin, and BPM2, which are to use it and cellulation and stimulate bone formation. Um, to evaluate biocalic response, human bone marrow stromal cells are used since they can differentiate into bone cells. Finally, in vivo models such as the CAM assay and mouse model are used to angiogenesis and bone formation in more realist environments. This slide presents the method used in the study. The method includes both in vitro and in vivo experiments, as well as material characterization techniques. In vitro analysis was performed to evaluate cell behavior of the scaffold. Cell viability was measured using VLR view, which indicate how well cells survive and grow. In addition, in addition, alkaline phosphate activity was evaluated to determine osteogenic differentiation. Sorry. Gain expression analysis was all perfect using PCR study the expression of bone relative genes. For in vivo analysis, the CAN assay was used to evaluate angiogenesis and biocompatibility. The test allows observation of blood vessel formation around to the scaffold. Additionally, a mouse model was used to analyze bone formation in a more realistic biological environment. Okay, finally, the material was characterized using different techniques. Scanning electron microscopy was used to observe the scaffold structure. Ferriti spectroscopy was to analyze the chemical composition, okay, present. And mechanical testing was perfect to evaluate the strength and stability of the scaffold. Okay, continuation. Okay, thank you.
In the results, the figure 1 shows the complete characterization of the PCL and TIMIA scaffold material. This structure is porous and interconnected, and the surface is not completely smooth because actually promotes the cell adhesions because it increases surface roughness. And finally, the geometry is reproducible thanks to stereolithography printing. In the panel C show the FTIR analysis of the printed scaffold, which allow us to identify the chemical groups on the material surface. The dominant peak corresponds to the carbonyl group, characteristics of the ester bonds presenting the polycarbonate chains. These confirm the material chemical identity. The most important point is the spectrum in the carbonyl group is present is small but detectable, indicating that very few metrical groups. And finally, this confirms that the degree of functionalization was greater than 95%, which tells us that the material polymerizes almost completely, giving it the desired mechanical properties. In the panel D shows the compression curve of the scaffolds. The blue line represents a different scaffold, and the similarity of these curves indicates the good mechanical reproducibility. The range of cancelable bonds between 100, 5, and 500 megapascals, so our scaffold falls within the lower range of that tissue. Furthermore, the scaffold withstood strains up to 15 to 20% before failure, which is approximately twice the maximum strain of cancellous bone, indicating that the material is more ductile than a natural bone. And remaining in the panel E shows the calibrated degradation study of the material. It utilizes sodium hydroxide at 37 degrees to accelerate the degradation condition that, for example, in the 7th day onward, a trend toward mass loss becomes noticeable, and in the day 21, the scaffold have lost approximately 50 to 20% of the original mass. And the smaller error bars indicate that the tree scaffold behaves consistently, and this result obviously is crucial because it confirms that PCL and TME is biodegradable. Okay, this slide shows the in vitro results for the cell viability and denudation of the PCL and TME scaffolds with the different bioactive coatings. First, in the panel B, we can see fluorescent microscope image of the human bones, stroma cells, and the scaffolds of the 2 time points, the day 1 and the day 14. The 4 columns represent the 4 conditions tested. Obviously, in the gray color, represents the live cells, and the red color represents the dead cells. And now in the panel A on the right, this bar graphic shows the alarma blue fluorescence results, which is surrogate for the cell number, metabolic activity. On the X, for example, in the X-axis, we have the 2 times point of day 1 and the day 14, and the G-axis, we have fluorescence in arbitrary units. They was finally as the highlight head and the bottom of this slide, 3 case messages for the results. First, outcoding support addition from the proliferation of human bone marrow stromal cells for the 14 days, confirming ex situ compatibility. The second, there was a significant increase in the solubility to the 14 days in the coated scaffold. And finally, in the third, the ELP coating showed an initial increase in ALP gene expression under baseline condition, while suggests early osteogenic signals even without osteogenic media supplementation. The formulation challenge is optimizing the BPM2. And why? The BPM2 activity is really dependent on the chemical environment and concentration, and the manufacturing is important to an inactive or active this BPM2. And the method and the correct method is for the low concentration, acidic environment, and the high concentrations, the neutral environment, or the name maybe is PBS. This slide represents the result from the chlorioallotonin membrane assay, also known as the CME assay, which was used to evaluate the biocompatibility, the vascular integration, and the angiogenic support to the PCL and TME scaffolds. On the left side, we can see 4 microscopic photographs. The scaffold placed directly on the chlorioallotonin membrane of chicken bryon and embryonic to day 14. On the right side, we have the histological sections trained with 2 different staining methods. The table is organized by coating types in row and by staining methods in column. The first column used alkaline blue and serious red staining, and the second column used golden staining. Summary said at the bottom left of the slide, 3 critical conclusions that I can see. We can see the successful angiogenesis and the anatomical integration is correct, and finally, biocompatibility. Okay, this slide shows the histological contrast between the collagen spawns, this is a control, and the PCL-TME scaffolds. First, in the top, the control group is the collagen spawn with a BPM2. It shows a clear and dense black and red ring, confirmed by the golden trichrome, and a disturbing red staining, which tells us that the real mineralized bone tissue formed around it. Now, looking at the bottom, the PCL-TME scaffold shows the grid tissue integrations around them. The tissue literally grows in the scaffold, but no formation was detected at all. So basically, the scaffold was really accepted by the body, but the subcutaneous environment just did not have the right cells to trigger bone formation. And this contrast is exactly what this use our conclusions. Okay, to do not delay the presentations, basically in this slide, I like to represent the implement size of the Murray subcutaneous model. You can see here more detail, but because in the past slide is the same information, in this slide is more broken down. And the only difference is that these are the results in an animal. Okay, the conclusion of the presentation of the inform it's 3. You can read the conclusions, but basically is the conclusion is enfocated to the 3 objectives of the inform, and in this past slides I to talk about different results because the ring is red, ring is black, because the subcutaneous will see it is be compatibility or not on the graphics, but the conclusion is basically resume this information that I can see you in the past slides. And finally, our recommendations of this inform basically is simple. First, improve the in vivo part because the material evaluation a real bone environment. Now it's an animal or now it's subcutaneous only because it's to a bone and it's important to evaluation in a bone. The second is optimize the concentration of BPM dose. I can use speak in the in past slides. The high concentration is bad to the experiment, but the low concentration is more better. But was it done systematically in the form. The third improve the mechanical properties, obviously, the best materials with some coating, etc. And finally, use a long-term study.